Hey, Physics 2011 students. I wanted to make sure and post a pretty detailed solution or video solution to the questions this week, considering that a couple of them were pretty math oriented. Um, and I figured this would be a good study resource for you. So, the group problems this week, the first question was a pretty simple question that asked us to connect back to what we had done at the end of chapter 7, which was looking at the work energy principle. And so just to uh, go back to, or connect back to where we were coming from in chapter 7. Come on, pen. Um, so in chapter 7, section 4, it was this work energy principle. And that was the idea that the net work on an object, on a particle, on something, is equal to its change in kinetic energy. And so use this, the first part of this question asks us to consider a situation where we have something that we're dropping out of a window. So a balloon dropped out of a window. And this is a problem that we could have tackled with kinematics way back in chapter 2. But now we're going to look at it from the perspective of energy conservation. And like I said, this connects back to what we looked at in chapter 7 with work, in particular the work energy principle. So how we use that in this case is we have to find the net work, and then that'll be equal to the change in kinetic energy. So when we talk about change in kinetic energy, really what we can think of is the kinetic energy final minus the kinetic energy initial. And if we're talking about an object that's dropped like this, then that means it has no initial kinetic energy because it has no initial speed. And so really the net work is just going to be equal to the kinetic energy final at the ground. And the net work in this case is just the work that's been done by gravity. So we can evaluate this, with our different definitions of work, but maybe force of gravity, distance, cosine theta might be the most logical one. And consider in this situation, so our displacement vector, let me draw this separately here. Displacement vector would be, from that height to the ground, so it has a length of h. And the force of gravity, of course, would be pointed down as well. So that means that the angle between these would be 0, and so this cosine factor would just give us 1. And that also means that the magnitudes of these would just be fmg times the length of d, which is h. And so the kinetic energy final is just equal to mgh. And mgh, we can actually put in our numbers here. The mass was 1 kilogram, 9.8, 6 meters. We would find that this kinetic energy would be about 58 joules. And then this also asks for the speed when it hits the ground. And we can get that from just noting that the kinetic energy final is equal to 1/2 mv squared. And so that means that the velocity would just be 2 times the kinetic energy over m. Take the square root. And, so we can put our numbers in here as well. 2 times our 58 times 1. We take the square root of this, and we would find that the velocity is about 10.8 meters per second. Yeah. Okay. The second part of this question asks us to use our definition for potential energy. So this was part A. part B. So the definition of potential energy is the negative work done by conservative forces. And the potential energy relative to the ground would be the work done by gravity to get from the ground to that initial height. And so that would be, well, we can work it out here. So negative force of gravity. Now notice now our displacement vector would be up because we're talking about to get to the initial height. And notice now that the displacement and the force of gravity are in opposite directions. So this would give us a factor of -1. And so when we work this out, we have negative, but we also have -1. So the potential energy is the familiar mgh. So it's just like what we've seen, and what you've probably seen before if you've tangled with any physics involving energy conservation. mgh is definitely a familiar sight when you're working with those kinds of problems. And then the last part of this question asks us to just set this problem up again in terms of energy conservation. And this is just to motivate that a lot of times it's just a little bit more straightforward to talk about it in terms of energy conservation. So how do we do that? Well, we're talking about just mechanical energy, so the sum of potential and kinetic. And so let me write this a little bit bigger here. That'll be the initial potential plus the initial kinetic will equal the final potential plus the final kinetic. And notice it has no initial kinetic energy, like we said, because it's being dropped. It has no final potential energy because if we set our coordinate at the system at the ground, the origin at the ground, then it will have no height. And so then we just have that the potential energy initial is going to equal the kinetic energy final. And notice this is exactly what we had from part A, except it's just a much more direct way of getting there. So when the question asks, do you notice any advantages or disadvantages? Basically what that's trying to get at is just that energy conservation is maybe a little more direct, intuitive, compared to, computing the work and invoking the work energy principle. So this is a very simple question. You'll see questions like this all the time where we're equating gravitational potential energy to some kinetic energy later. And so this is a good place for us to start. Now, the next question in here is basically a math question. And this is asking us to get at potential energy given a force. And to do this, we have to understand that the potential energy, again, is the negative work done by conservative force. And so the force that we have in this case is this sine function. And notice this is pointed in the I-hat direction. So when we go to evaluate the work, i.e. negative F dot dl, the only direction that's going to contribute to the work is going to be dx. And so this will become negative integral f of x dx. Any contributions in any other directions would give us 0 since this force is aligned entirely along the I-hat x direction. It tells us that a and k are constants, and so we basically have this indefinite integral of a sine kx. And the one other piece of information that we have to make use of is that there's a boundary condition where the potential energy is 0 at x equals 0. And notice, just to clarify, I've written PE here for potential energy. Your book uses the letter U. We'll use them both because they kind of crop up. All right, so all we have to do then is integrate this and make sure that the potential energy equals 0 at 0. Okay, so all we need, notice this a would come out because it's constant. So all we need is the integral of sine kx. This is an integral that you should be able to do. The integral of that would be negative cosine kx over k. And you can check yourself with this if you're less comfortable with your integration by just going the other direction. So if you take a derivative of this quick of cosine kx over k, cosine would give you negative sines, so our sines would cancel. And then you'd pick up a factor of k, so the k's would cancel, so you'd be back to where you started, sine kx. And then since this is indefinite, you would also have a constant here, c. Okay, so that's the general expression for the potential energy function. And we need this at 0 to equal 0. So in order for that to happen, let's see what happens here. So these negative signs cancel each other out. Cosine of, well, here, let me just actually write it out. So this would be a cosine of 0 over k. So this would give you 1 plus c must equal 0. So that means a over k plus c must equal 0. So therefore, c must equal negative a over k. And so our final solution for this question would be that the potential energy function is equal to a cosine of kx over k minus a over k. So this is a fairly straightforward question, but it involves integration, and integration is one of the things that I know folks have a different amount of background with. So this is a kind of function that you should be able to do. So actually, let me just put a note here. With regard to integration, you should be able to do, polynomials. You should be able to do sines, cosines, etc. But I'm not going to, product rule, quotient rule. But I'm not going to ask you to do like exotic functions or anything, much more complicated than that you would be crunching in your, in your calc classes. So, moral of the story, to connect back to why we care about this, this shows you how you get the potential energy out of a force by computing the negative work of that conservative force. And this is just an example of applying that. So, the next question goes the other way. So, up above, we were talking about how you can get the potential energy out of the force. Well, suppose you have the potential energy and you want the force. You can go the other way. And to do that, you need to take a special kind of derivative called the gradient. So notice potential energy would be a scalar, right? Force is a vector. So this operation, computing the work, takes those vectors and gives us a scalar quantity. If we go the other direction, we need to get a vector out of a scalar. And the way that you do that is with this vector differentiation operation called the gradient. So what this operation looks like is it's a combination of partial derivatives. Actually, there's a negative sign here too, sorry. It's a combination of partial derivatives and plus the unit vector, or times the unit vector along that direction. So looks like this. The partial of x along I hat, the partial of y along j hat, the partial of respect to z along k hat. And you need to apply this function to your, or apply this operator to your potential energy function. You can think of this as being in general a function of x, y, and z. And this will tell you the force. And conceptually, you can think of this as, imagine the energy is like a surface, and where the surface is changing, if it's changing a lot along that direction, that means that there is a force along that direction. So this question asks us to do this operation for this function, u of x equals negative ax over b squared plus x squared. And so let's do that. So we need to basically take this derivative of that. And the first thing that I would draw your attention to is notice this thing is only a function of x. So what that means is that this is going to simplify to be only along x, because the derivative of this thing with respect to y and with respect to z is going to be 0. And so this force would just become a force along x, partial derivative with respect to x of this times factor of I hat. So if you're unfamiliar with partial derivatives, think of this as just the derivative with respect to, whatever x or y or z or whatever, while treating everything else as if it's a constant. So when you go to take a derivative of this with respect to y, it's like it's a constant, and so it's 0, the same with z. So let me just make a note here. So let's take this derivative. We'll have the derivative. So this is a quotient. And actually, I forgot here, we have our negative sign. Whoops. So we would have a negative sign here. So let's note that those negative signs would cancel. And so the derivative of this top bit, so low d high minus high d low over the square of what's below. This d high would just give us factor of a. And then minus I d low would give us a factor of just 2x all over the square of the denominator. Notice we would have b squared a plus x squared a minus 2x squared a. So this term and this term we can combine together. And so this would give us b squared a minus a, let me just write x squared a over b squared plus x squared quantity squared. And so this would times in the I hat direction, and this would be our force. So this is the purpose of this problem is just to drive home how if you have the potential energy, you can get the force out of it as well. So this kind of complementary operation, we can go from force to potential energy by integrating the force or finding the work, in other words, and we can go from potential energy to force function by taking the gradient, this derivative operation. So hopefully this just emphasizes to you that these two different kinds of problems that are really calculus problems, but we're actually worried, we're trying to compute quantities that we care about in physics, potential energy and forces. All right. The last question that we had looked at was a little bit more complicated energy conservation question. So why don't we walk through the solution of this one as well, just so you have it for your reference, because we weren't able to spend as much time on this as I was hoping in our synchronous sessions, so I think it would be nice to have a solution that you can refer to if you so desire. So this question is a little bit more complicated than the first one because it asks us to make use of two different kinds of potential energy. So we know the potential energy due to gravity, that's just mgh, but there's also the potential energy associated with the spring. And you can get that by taking the negative work associated with the spring, i.e. integrating the spring force. And if you do that from some initial spring length to some final spring length, you would find that the potential energy from a spring is 1/2 kx squared. So this problem requires us to make use of both of these types of potential energy. Okay. A couple other things that I would draw your attention to. Notice the way that this problem is set up. The coordinate system y equals 0 is in the middle, which is kind of interesting, but you'll see that that's actually kind of convenient. It doesn't have to be that way. You could set it down here if you want, or you could set it down here, or you could set it down up here. As we've discussed before, the coordinate system is kind of arbitrary. What really matters is the change in potential energy, but you can see with this that this will make things kind of simple if we set it there. So we'll run with that. The other thing that I would recommend with this is, you can break this into parts. So like let's just call these A, B, and C. Basically, we can apply energy conservation between A and B and between B and C. And that can be a way to be kind of pretty methodical about breaking down the problem. So let's have at it. We're going to note that the potential energy, so conservation of mechanical energy, potential energy plus kinetic energy at A is going to equal the potential energy plus kinetic energy at B. Now notice, according to this coordinate system, and given the fact that this starts from rest, it will have no kinetic energy at A, and then at B, it will have no potential energy because it has no height and it has not compressed spring. Okay, and then between B and C, so just being really methodical and noting all the parts, even though we know that this one is 0 already. Notice at the end, since it comes to rest, the spring has caught it. This would be 0. And what we have said here is that the potential energy at A is equal to the kinetic energy at B is equal to the potential energy at C. And so we don't even need to know the kinetic energy in the middle to note that the potential energy at A is equal to the potential energy at C. And so let's put in those energies and solve for K. So I should have mentioned before, ultimately what we're looking for in this question is to find the spring constant. So just determine the spring stiffness constant here, so K in other words. So what's the potential energy at A? According to our coordinate system, it's mgh. Potential energy at C. So notice it's going to have two parts. There's going to be mgh, but instead of h, it will be negative y. It has a negative height relative to this coordinate system, where y equals 0 in the middle. And then the other part is going to be the potential energy due to the spring. So that'll look like 1/2 k negative y squared. Notice, since it's squared, the spring potential energy doesn't matter if y is positive or negative. It stores energy in either case. And then we would just need to solve that expression for k. So let's do that. mgh plus mgy have a factor of 2 divided by factor of y squared would give us k. Let's put in our numbers here. So what's the mass? 2.6 kilograms. factor of g. The heights, so we have 0.55 meters and 0.15 meters added together. And then this would all be divided by 0.15 quantity squared, 0.15 squared. And you crunch the numbers, and you would find that the spring constant is 1585 newtons per meter. So this is a good question in that it gets at a little bit more complicated. Actually, let me round this to 1590, just given we have three significant figures. This gives us an example of making use of both potential energy stored in a spring and in gravity, and shows how you can make use of the coordinate system to make things convenient. So yeah, I wanted you to have access to solutions to the questions that we looked at, so hopefully this is a helpful resource for you. And